Okay, Assalamualaikum. So this is CHEN 1210, Organic Chemistry, Semester 1, 2023-2024. So we have 20 slides together and I will mix Malay and also English. So sometimes saya cakap dalam bahasa Melayu, sometimes saya cakap dalam bahasa Inggeris depending on the situation. The most important thing is that you should have prerequisite knowledge. You know what we have learned before in order for you to follow along this video. About this video slide, I already upload it in the master sheet for your reference. So we start with the curly arrow first. Okay, I always talk about the curly arrow because why? Because curly arrow allow you to draw a mechanism on the reaction even though you don't know anything about the reaction. For example, this reaction, you know nothing about this reaction, but then you still can draw a mechanism based on the curly arrow understanding on this lah. So for example, this is Me. What is Me? Me is the metal, so CH3. I is what? I is iodide. What is PH3? PH3 is a phenyl. PS stand for phenyl. Phenyl is basically the aromatic compound like this. You have the substitution of the aromatic compound, and Phe is a phosphorus, and this is just the product. So what will happen in this reaction is that metal here will make a bond with the phosphorus and break the bond with the iodide. So that's what will happen in this reaction. So now, in order to draw the mechanism for this reaction, you need to first draw all bond clearly. Okay, if you look this MEI, it's not very clear what is the bond. So you need to draw clearly like this. Okay, so you have a bond there. Okay, same with this PH3P. We don't see any bond, so you draw clearly like this, so you can see the bond there. And then ask which one is nucleophile, which one is electrophile. In this case, phosphorus has lone pair. Okay, so lone pair means that you have a extra electron that is non-bonded to anything, which is ready to bond with something. So in this case, phosphorus here is this thing will become a nucleophile, and the bond here, if you look at the metal iodide, you have the electronegative element, and this electronegative element will somehow pull the electron density toward itself, causing this bond susceptible to attack by nucleophile lah. So this will become the electrophile. Okay, so now how to start the mechanism? So you start the mechanism. Let me remove the color first, the addition first. So you start the mechanism with the source of electron. We know the source of electron in this case is the what I call nucleophile, so the lone pair. So the lone pair will attack the electrophile, and when you do like this, what will happen? You create a new bond. You create a new bond, meaning that some bond sometime will be broken lah, because if you do like this, if you make a bond like this, you already have the phosphorus already make 1, 2, 3, 4 bond. If you don't break this bond, you will end up like 5 bond like this, 1, 2, 3, 4, 5, if you don't break this bond. Okay, so this what could go wrong lah. Okay, so you need to understand, when you attack something, you need to ask whether if I make a bond, is there any bond should be broken, or there are no bond should be broken. In this case, when you attack with the lone pair to the electrophile here, another bond on the metal iodide must be broken. If not, you will end up with this. This is impossible structure because carbon have 5 bond. We know for carbon it's only have max 4 bond, okay, to fulfill the octet. So that's the reason when you do the mechanism, you need to not only one step. Sometimes you need to know that one step of pushing the arrow from one side to another, does it cause another bond to be break or not? Okay, so if you look here, boron, carbon, nitrogen, and oxygen never have more than 4 bond. If you make a new bond to uncharge whatever this thing, you must also break one of the existing bond in the same step. Okay, so that's important. If not, it's not. If you don't do that, it's not possible lah. Impossible structure will be yield. Okay, so now next example, this reaction. Okay, you don't know anything about this reaction, but then you can still make a mechanism. You can still draw the mechanism. You can still draw how the arrow move from one side to another. Okay, so what is this? This is a carbonyl compound. Okay, but now we know this thing. This is just a carbonyl compound. This is just the product of it. But what is this thing? Okay, NaCN is an ionic solid. Okay, so you can see there are sodium and also the cyanide. So the true reagent here, because ionic solid, remember this solid, when you want to do this reaction, normally you put in water, you can see there are water there. So when this thing, any solid is like NaCl lah. When you put, this is salt, okay, when you put in the water, what will happen? The NaCl will be dissociate to Na plus and Cl minus. Similarly with this, NaCN is also a solid, behave like the NaCl salt. Okay, so when you put it in the water, what will happen? It will be deassociate. So the true reagent here will be cyanide ion. Okay, because you have Na plus and then Cn minus. Okay, now we want to talk what is the nucleophile or electrophile. We know the Cn, the cyanide is what we call the have a lone pair. Actually, they have two lone pair there. So the cyanide here is will become a nucleophile. So the true reagent, the true reagent here mean what actually become the nucleophile that's attacking the electrophile in the reagent. Meaning the true reagent lah. It's not the entire thing. It's just this thing lah, because this is the one that will be participate in the reaction. So okay, there's too much there. So let me remove this thing, erase. So let me remove it. So this is cyanide. So you can see cyanide. So this we have learned before actually. Just to recap a little bit. So cyanide ion. So you can see you have a lone pair here, lone pair on the C, lone pair on the N, and then you have the what we call this negative charge here, constitute two extra electron. So the sp orbital for the carbon is higher energy than more electronegative nitrogen. Therefore, lone pair on C is HOMO. Okay, what does it mean here? Okay, so you have two lone pair. So now, which lone pair will attack? Is this lone pair or is this lone pair? Okay, so in order to know that, we need to see the situation of this lone pair. The carbon and nitrogen is more electronegative than carbon. So meaning that when this is more electronegative, they will attract more electron. When it's attract more electron, meaning that it will be more stable, because more electron meaning that you can feel the space or the orbital better. So meaning that it become more stable. Okay, when it's more stable, if you have energy diagram like this, you have energy diagram more stable. If you have full electron field in the orbital, we call it stable lah, stable. But if you have another level, you have electron, but that's higher in term of energy level, this thing is unstable. Meaning that it can go out, it can, much easier for this electron at that higher level, energy level, to get out from this orbital. So this is what we call HOMO, higher occupied molecular orbital. Higher energy occupied molecular orbital. So if you compare A and B here, B is constitute the HOMO. Okay, so that's why if you compare the carbon and nitrogen, carbon here become HOMO. So that's mean this thing, the what we call the electron pair from the carbon, is the one who will attack. Okay, even though they are both have lone pair each one. Okay, so that's the thing. So nucleophile, carbon anion, electrophile, the C. Okay, so we have done with this carbon anion. We understand why it become the nucleophile. But let's look at the electrophile. So the electrophile here, if you look here, and the carbon here, okay, the carbon here. So the carbon here also attached to the electronegative element. So this electronegative element somehow will, what we call, will pull the electron density up. So meaning that this carbon here, the one that I draw the arrow here, is somehow deficient in electron. Okay, so much easier for this carbon to be attacked by the nucleophile. So that's why this thing, the electrophile, is the carbon at this carbonyl group lah. Okay, so let's start the mechanism. Okay, let's start the mechanism. Let me remove the drawing first. Is to, let me erase. Okay, let me erase this first. Okay, let me erase this first. Okay. So it must be easier for you to see lah. Okay, now pen. Okay, now, okay, let's start to draw the mechanism. What will happen? So the charge here, the negative charge here mewakili dua electron, will attack the electron deficient carbon here, the electrophile. And as we mentioned before, when you make a bond, you need to ask whether there are another bond to be break or not. Okay, so in this case, when you try to attack here, you will make another bond here, C, but now you have 1, 2, 3, 4, 5. So you know that when you draw the arrow here, some bond will be made and some bond will be broken. So which bond will be broken is this one lah, is this one in the top one. So let me erase here. Okay, so like that. Okay, pen. Okay, okay. So now, so when you do like that, you get something like this. Okay, so when this thing, what we call, when the arrow, this is basically what will happen here. The thing. Let me erase first. Okay, it's not very clear there. Okay, so when this, what does it mean by this is that the two electron, because remember the arrow here, the mechanism arrow, this arrow means that it will bring two electron with it. Okay, so mean that where is this two electron come from this double bond, the pi orbital. From this pi orbital of the double bond, it will go to the O. So what will happen, the O will receive extra electron, so that's why you see the minus here. But remember, we have learned before that the product, the reactant, and also the product for any reaction must be conserved, meaning that if the initial reactant is what we call is non-charged, the product also non-charged. Okay, it must be, the charge must be conserved. So you have the negative charge here, so you need to sort of like make it like neutral back lah. Okay, so what will happen, the anionic oxygen, this anionic oxygen pick up proton from somewhere. Okay, anywhere lah, from the, normally because we do in the water, so they will pick up the water from the hydrogen from the water lah. So you can see here, this is the reaction, the anionic oxygen will pick up the hydrogen from the water. And what will happen when you pick up, what does it mean? It make a bond. So when it make a bond, you need to ask whether another bond need to be broken or not. In this case, true, it need to be broken, as the same analogy like before lah. So then you get this thing. Okay, okay, now next reaction, we have ethanol as a starting material and the ether as a product, and there's proton as a condition. What is a proton? Proton is the acid. So this is acid catalyzed reaction. So even though you know nothing about this reaction, you can still draw the mechanism. How so? By knowing what is the nucleophile, what is the electrophile. What is the nucleophile for this reaction? So we know this ethanol have a lone pair, two lone pair there. So this should be the nucleophile, and the electrophile, it should be this proton, because why? The proton doesn't have electron at all, so it's easily become the electrophile. Okay, so we establish that, then we do the mechanism. How? By showing that nucleophile attack the electrophile. So we have this lone pair from the ethanol attacking this proton, making the bond here. So I want to talk a little bit about this what we call the positive charge here. If you see this ethanol, they don't have charge. Here you have charge. Here the what we call this the proton also have charge. So what this mean? Okay, so if you look this thing, if you look the ethanol here, so even though you have two lone pair there, by right they have another lone pair there. Okay, so if you count the number of what we call the total electron that bond to the oxygen, you can see there are 1, 2, 3, 4, and the bond, each bond meaning that there are 2 electron, 5, 6, 7, 8. So oxygen is happy, this octet, there are no charge. Okay, now let's see about the hydrogen. Okay, let's see the hydrogen here. So the hydrogen as plus. So we know hydrogen is basically the hydrogen itself is a atom with the electron, 1 electron. When you have plus here, what does it mean? There are no electron at all. So the hydrogen is empty. So we call as plus, the proton is basically empty orbital, meaning that if you draw the energy diagram, so there are nothing on this orbital, there are no electron at all. Okay, so now let's look at the ozonium ion. Okay, so if you look here, O, H, and then H, and we know they are still the lone pair there. So if you count the number of what we call the number of electron in this, you can still see 1, 2, 3, 4, 5, 6, 7, 8. They have 8. So should be octet. But then why they are positive charge? Why they are positive charge? The reason for this is because of this. It's because of this issue. Okay, because when the ethanol make the bond with the hydrogen here, the bond is basically here. The bond here, the particular bond here, is basically made from the electron coming from the oxygen alone. Okay, so when you make bond with the hydrogen, hydrogen doesn't share anything, just accept it, doesn't share anything. So as if now the what we call the oxygen now, they're feeling that this particular electron here is already still by the hydrogen. So oxygen feeling that is have one electron deficient. Okay, so that's why you have positive charge there. Okay, so positive charge here, positive charge for the oxygen here is not the same as the positive charge for the hydrogen. So here, if you draw the what we call the energy diagram, if I can put this as a energy diagram for this particular area only, you can see that there are only one what I call one electron there. So for I mean looking at the oxygen there are only one electron, because another one as if the hydrogen already steal it. Okay, so there are one electron for this oxygen, so it's not octet. So that's why you have plus there. So if you compare these two, this thing, so the H plus and the oxonium ion is not the same. Okay, so this is empty orbital, whereas the oxonium ion is not empty orbital, and this have a consequence. When you have empty orbital, the nucleophile can enter, because remember, nucleophile meaning that you bring 2 electron, so 2 electron can go inside this. Okay, but when you have something inside the orbital, then you cannot enter easily. 2 electron cannot enter this thing, because you have this what we call some electron, because one orbital can occupy max 2 electron only. Okay, so just to show that this H plus and oxonium ion, the plus there is not the same plus. I mean the positive charge there doesn't mean the same thing. Okay, for the proton is empty orbital, for the oxonium is not empty orbital. Okay, so let me remove all this ink. Okay, let's go next. Okay, positive charge oxonium ion here has to be electrophile. Okay, so you can see this oxonium ion, you have positive charge, but then it's not still the product yet. Okay, remember, the product must be same as the reactant in terms of charge. So reactant here have no charge, so the product also must be neutral charge lah. So we know that there are another step involved. Okay, so being positively charged also mean it can act as a electrophile, because electrophile mean deficient in electron, so something can attack it. So oxonium ion can behave like the electrophile. So what is the nucleophile? So the only possible nucleophile is another molecule of ethanol, but we got the dilemma there, because first, if the lone pair of the another molecule of ethanol attack the what we call the bond here, what will happen? When you attack here, when you make a bond, another bond must be broken in order to what we call to preserve the octet rule. So if this thing broken like that, this thing it become something like this. It become lone pair again, and then there are another lone pair, the original lone pair that is not shown here. So it become ethanol again. So it become the same as a what we call as a original. So you just get back where you started lah. If you try to attack the lone pair, try to attack this thing, the bond. If let's say the another ethanol try to attack this positively charged oxygen, there also problem, because why? Because it's not empty orbital like we explained before. Okay, if lone pair attack positive charge oxygen, we got oxygen with 10 electron. Okay, so meaning that the reason is same like we discussed before, but this just what I write on the slide lah. But the idea is the same like what we discussed before. Why you cannot attack this positively charged oxonium ion at oxygen, because it's not empty orbital. When you attack it, when you make bond it, you basically make more bond. You make like extra bond, which is which what you call violate the octet rule. Okay, so now what's the problem? So now what is the solution? You cannot attack here. You cannot attack on the OH bond. You cannot attack on the positive charge oxygen. So how we want to remove this charge here? Okay, so the solution is that by attacking the carbon bond. Okay, let me remove the color here, the ink first. Okay, so the solution is that the lone pair must attack at carbon. Okay, the lone pair here, whatever the lone pair here, they attack at carbon here. Okay, so let's see why is attack at carbon. Because remember, you know the energy diagram. When we draw the molecular orbital, when we learn about molecular orbital theory, let's say we make a bonding, it can be bonding, and also it can also be anti-bonding, right? Okay, normally bonding happen when what we call the bonding molecular orbital fill with the electron, two electron, then you get bonding. But then if let's say another electron come and fill up the anti-bonding, they will cancel out. Okay, so that's what happened here. So remember this thing, the carbon here, the carbon, let me put another color lah. Where is the another color? Okay, the carbon here is only make a bond with the oxygen. It's only make a bond with oxygen, as if now the sigma, the what we call the sigma bond is already filled with the electron. When the nucleophile attack here, attack to this what we call this carbon here, it can only fill up the anti-bonding part. Okay, they can only fill up the anti-bonding part. So the electron here goes here, what I call the green one, goes here. So what will happen? It will break. It will break. That's why now when you attack here, this thing will break. It will break. So it will go to ni lah. It will break. When you make a bond, something will be break lah. So that's why. So when this break, it will go here. The what I call, because when you break, meaning that the electron will, when you break the bond, doesn't mean the electron disappear. The breaking the bond meaning that the electron goes somewhere else. So for example, you have 4 electron there. So when you break, mean that 2 electron go somewhere, 2 electron go somewhere. So the 2 electron, this one will go to the oxygen. Okay, will break, will go to the oxygen. So you get S2O lah, because S2O is basically H, and then you have oxygen there. So that's why you get S2O here. This thing. Okay, you get this thing, and then when you make, so the whatever this thing make a bond to this thing lah. When you make a bond, so this make a bond, you get this lah. You get this. Okay, so that's what does it mean by this. Okay, so now when you make a bond, this become positive charge again. Okay, but now this thing, it can sort of like putting electron and possibly molecule converter, and then now what will happen next is that the last step is loss of proton to give the ether. The proton here will be lost lah. Will be lost to give, because it is positively charged, and the proton will be lost lah. So you get this ether. Okay. Okay. So you might ask, okay, if the proton here can move there, why not here they do the same thing? Because if you can do that, but then the problem, you don't get the ether. The question now is that how this get this. Okay, if you do like this, if you if let's say this, it can go here. Of course it can go here, but then you don't get that ether. So we want to show the mechanism so that it can fit this reaction. So that's the reason. Okay, let's talk about the arrow in organic chemistry. You have seen the curly arrow, you have seen the straight arrow, that is a mechanism and reaction arrow. For example, like this is a mechanism arrow, this is a reaction arrow. Sometimes you see a double arrow. Double arrow means equilibrium arrow. What does it mean is that it's a reversible reaction. The reaction can be reversible, and this, what we call this double arrow, can be equal length and this difference length. Okay, so what does it mean by reversible? It doesn't mean that the reaction, for example, let's say I take here, it doesn't mean the reaction from the aldehyde to the hemiacetal happen, go back and forth, back and forth. No, it's not like that. It means that you can tip the equilibrium depending on what you want, depending on the condition. For example, let's say aldehyde to hemiacetal. Let's say if hot, you get hemiacetal. If cool, the hemiacetal will go back to the aldehyde. So it's like that. So depending on the situation or condition of the reaction itself. Okay, so you need to tip the equilibrium yourself. It's not like happen automatically. It's not go back and forth. Okay, you see the equal length of the double arrow, meaning that the same stuff can yield a new product and can return to original reactant easily lah. Okay, by tipping the equilibrium. When you see a different length like this, for example, one arrow, so this is half arrow. You see this half arrow, not the full arrow. Half arrow. So when you have a different length of the equilibrium arrow, what does it mean? The side with the longer, let's say this one, let me put the different color. This one is a longer than the bottom one. What does it mean is that the product, in this case, you see the longer arrow going towards the product, mean that the product is more favored. Okay, when you do a reaction, the product, most likely you will get the product, then the is much more favorable to become a product rather than going back to the reactant. So that's what does it mean lah. Okay, single arrow with two head. Okay, single arrow with two head, delocalizing arrow. So this one. Okay, so this is single arrow with two head. So this means delocalization arrow. We have learned this before in the previous class, in the physical class. So it's implied the resonance structure, resonance structure where each structure exists at the same time. So when you see something like this, okay, when you see something like this, double arrow, okay, double arrow, but two heads like that, it's implied resonance. Resonance mean that the thing occur simultaneously. For example, if you have 1 and 2, it doesn't mean the 1 and 2 go back and forth. Okay, it means that 1 and 2 exist at the same time. Okay, but because we cannot have like what we call the drawing to show that in drawing, then we do like this lah. Okay, for example, for benzene, it means the electron no longer localized in specific double bond, mean that there are no double bond like this. The double is not really a double bond actually. It's in between double bond and single bond for benzene lah, because this what we call the concept of delocalization lah. Okay, so somehow the electron sort of like spear or smear or delocalize all over the 6 atom in the ring. So you have 1, 2, 3, 4, 5, 6, as if the electron now, because remember double bond means that there are extra electron. So as if now the electron, when you are in this delocalized condition, the electron here does not fix there, does not fit here. It's as if they are sort of like smear around all the 6 carbon, but we cannot have what we call drawing like that. We cannot draw something like this. This is so strange. That's why we draw something like this. Okay, just to imply that this thing imply that the electron is delocalized. I mean, it's like sort of like smear around all the 6, 1, 2, 3, 4, 5, 6 carbon lah. So this is normally true for the benzene lah. Okay, it does not mean that there are 2 separate structure. It does not mean that the 2 structure are changing back and forth. Okay, you need to be careful, be know lah about that. Okay, here you can see that there are the arrow here. This is not what we call, this is not mechanism arrow. When you see this delocalization, you just want to show that the what we call, just to show that the electron can move here and that, not the mechanism, but rather than to show that the electron is not fixed in one place lah. Okay, in front of you now is the functional group that you commonly see in organic chemistry. So we start all with the what we call with the hydrocarbon. So you can see hydrocarbon mean that you have hydro, which is hydrogen, and also carbon, which is carbon. So this hydrocarbon you can have either single bond, double bond, triple bond, alkane, alkene, alkyne, or you can make the cyclic like this thing. And this cyclic is special because you have this conjugated nature or delocalized nature of this cyclic 6-member ring of arene. So this is what we call benzene lah. So so if this becomes substituent, we call it phenyl. Same like when you have alkane as a substituent, we call it alkyl. Same idea. And then this is without any functional group lah. But when you have functional group, you can have either halide, oxygen, nitrogen, and this carbonyl. So alkyl halide is basically represented. Sometimes people represent alkyl halide like this X, where X represent a halogen. Alcohol is what we call also called hydroxy group, the OH. The ether, instead of OH you have R. R here denotes the what we call anything. R can be anything. It can be hydrogen or carbon, but normally R here denote the carbon lah. Because why? Because if this R here is H, then it become alcohol. So R here normally is carbon or alkyl group or whatever lah. Reactivity of organic molecule is so dependent on the functional group that the rest of the molecule can be irrelevant. That's why we put R here, because we don't care. Because if this R is alkyl group and then you have the O there, if you do reaction, what really react, what will sort of like do participate in reaction is mostly this O lah. Okay, so that's why R is somehow we put just R rather than we put the entire structure of the alkyl. Okay, and then we have amine, nitro, nitrile, cyanide. You have the nitrogen there, and the carbonyl have sort of like same pattern. You have CO, the carbonyl, the CO, CO, CO. So aldehyde, you have the hydrogen, aldehyde H there, and the ketone you have both are alkyl group or whatever group. Carboxylic acid you have O and then H, and the asaccharide you have chlorine, and the ester is same like the carboxylic acid. The difference is that you have the R there instead of O, instead of H, and then you have amide, you have nitrogen lah. And then this is what we call acetyl and amiacetyl. So the difference between these two is that you can see this and this lah. Okay, people call it hemiacetyl because hemiacetyl is halfway to acetyl. You can convert hemiacetyl to acetyl by what we call the substitute this OH group, the hydroxy group, with the another R group lah. So you get the acetyl. So this also we call it functional group lah. Okay, the R, about the R itself, you can see sometimes I put the, let me put the color, different color. You see I put, sometimes I put the, what we call the prime there, the prime, right? Sometimes they are numbers. Okay, it doesn't really matter actually. It's just to show that these are different R only. So it doesn't really matter whether you put prime or you put numbers, whichever you easy for you, that's you can do lah. One more thing is that about the how to you denote something. For example, you have alcohol. Sometimes you heard people say primary alcohol, secondary alcohol, tertiary alcohol. What does that mean? So primary carbon is an atom attached to only one other carbon atom. Okay, so for example, let's say this carbon they attach only to one carbon, so we call it primary carbon. But because this alcohol, then we call it primary alcohol. Okay, so it's not unique to alcohol alone. It can be other thing, for example carbon or whatever. Okay, for example, let's say this thing. So this carbon here attached to another 3 carbon. Okay, so that is tertiary, but then this alcohol, so we call it tertiary alcohol. Okay, let's talk about carbonyl group. Carbonyl group, when you have the carbon attached to the oxygen, so you have this pattern, and this pattern is prevalent in other carbonyl group. For example, aldehyde, ketone, carboxylic acid, ester, amide, and acyl chloride. And this carbonyl group is undoubtedly the most important functional group in organic chemistry, so we need to know a little bit more about carbonyl. So carbonyl double bond consists of 2 parts, the sigma and also the pi bond. Okay, so you have this carbon and then oxygen, and then you have this what we call the this thing, this double bond. So double bond here is basically sigma plus the pi. So sigma is basically head to head, so either you have s orbital and or p orbital head to head interaction overlapping, and pi is basically when you have this the side by side overlapping of the p orbital. So carbonyl double bond have this thing lah. So that's why you can see this thing, this is sigma, and the top one, this the green one here is basically the pi lah, the pi. You have top and bottom. Okay, so this is sp2 carbonyl group adopt the sp2. So basically this carbon here is sp2, sp2, sp3. sp is basically just the hybridization of the carbon which dictate the structure. For sp2 the structure will be planar. So sp2 mean that the carbon attached to 3, so and then it's planar, mean that it's like this, and then they have this what we call the gap between this angle is 120, 120, 120. So if you have sp3 like a methane, then you have this tetrahedral structure. So the hybridization will dictate the structure. Okay, and the sigma bond, this sigma bond between the two sp2 hybridized atom, carbon and oxygen. Okay, so what does it mean? This is sp2 hybridized. Let me put the other color lah. This is sp2 hybridized. This also sp2 hybridized lah. So the what we call this? This is sigma bond is between two sp2 hybridized carbon and oxygen. That is sigma bond. So this, what does it mean here? One is here, and then the other sp2 orbital of carbon form two sigma bond to the substitution, meaning that this sp2 carbon is also make this two. They also make this lah. Okay, and then lastly the other sp2 orbital of oxygen, because remember the oxygen also is sp2. In this case, this oxygen also is sp2. They remember the oxygen here, they have lone pair. So this lone pair, how they what we call, they behave in this orbital. You see here they are also sp2. I mean that they are 120 degree like that, the angle here there, because the other sp2 orbital this lah. What does it mean? Okay, polarization of the pi bond means that it's skewed to oxygen. Okay, remember pi bond is what? Pi bond is basically this. Okay, this thing. Okay, and pi bond can be pi bonding or pi anti-bonding. Okay, so polarization of pi bond, the one that is manifest is pi bond, so meaning that it's bonding lah. So it's skewed to oxygen. If you have CO, so it's skewed toward this lah. So the pi bond is basically more here. Okay, but the anti-bonding pi is just the reverse. So if you have C, so this anti-bonding pi bond is here. Okay, so that's the picture lah. So let me remove all the what we call all the ink, so you get something like that. Okay, because it's hard to represent both pi and pi anti-bonding together, it become easier to visualize individually. So it's just like what we call a piecewise lah. They do individual, this anti-bonding, and also this is filled pi orbital lah. Anyway, okay, so now if we want to talk about the reaction of carbonyl group, we need to recap a bit again about the electrophile and nucleophile. So this is nucleophile, this electrophile. So we have explained this in detail before in the class. So hopefully this just for what I call recap only. So you can look lah. The nucleophile can be lone pair, negative charge, double bond, pi sigma bond to electropositive atom. So electrophile can be the proton, can be this empty orbital, can be this what we call double bond to an electronegative element. Okay, so you look here, it's more like the carbonyl group, carbonyl. So yeah, so that's why the carbonyl can be the electrophile lah. Most likely become an electrophile, and also can this single bond to electronegative element. Okay, let's talk about the reaction of carbonyl group. Okay, the first we talk about the attack by cyanide. Okay, cyanide is the most important carbon nucleophile. We have learned this before. So just to recap, this is cyanide ion. So you can see the cyanide ion have this lone pair. So he have negative charge. So this negative charge, or what we call this, representing 2 electron. Okay. Nucleophile atom is usually anionic carbon rather than nitrogen. And we have basically this thing we already discussed in the beginning of the what we call of this video. We talk about why this this what we call the lone pair on the carbon is the one who are attacking the electrophile. Is because the nitrogen is more electronegative, so it's more stable, meaning that it's not HOMO, it's not highly occupied molecular orbital. Okay, we have discussed this. If you forget about it, please refer back to the earlier discussion on this. Anyway, so this I just skip. Okay, anyway, look at this, what we call at this reaction. Okay, so what is this reaction? Okay, if you look here, nucleophilic addition of cyanide followed by protonation of anion. So if you look, this is what we call the carbonyl. Okay, so normally if I draw like this is basically the shortcut. I mean, what is the overall reaction? But the actual mechanism is this way. Okay, so just to let you know lah. Okay. Okay. So a nucleophile addition of cyanide followed the protonation of anion. So for example, you have this and then you have this charge. Charge is nucleophilic, attack the electrophile carbonyl group, and then when you attack, something will sort of like break out. So when you break out, you get the negative charge on the oxygen or say an ion, and then this negative charge it will catch up, it will attack another hydrogen, another proton. This proton here is basically is given by this what we call either from this H2O, you can get the hydrogen from this acid also you can get. Okay, it doesn't matter where you get the hydrogen, doesn't matter. You know that this what we call this oxygen ion will make the bond with this protonation will happen lah. Protonation will happen, and then when protonation happen, you get this as a final product. So in general, addition to carbonyl group consists two steps. First, nucleophile attack on the carbonyl group. So this one is basically this. So this one is this. Okay, and then you have protonation of anion. That result, this one is this. Okay, this is what we call protonation. Protonation means that the addition of proton. For example, this O, you want to add the proton. You want to sort of like to attack the proton. That's protonation of anion, that result. So this is basically when you talk about carbonyl group, this is generally the reaction of that. When you have the addition, you have the addition here, and then you have protonation of an ion. Okay. Okay, why nucleophile attack the carbon atom of the carbonyl group? Okay, the question here, why the nucleophile here attack, let me put the color lah. Why the nucleophile here attack the carbon here? Okay, so that's easy because the carbon and O, you have this polarized, and then as if now the carbon here deficient in electron. So yeah, that's the answer. It's much easier. It's easy. Polarization of antibonding. So this, if you want to go more detail lah, mechanism. So mechanism, this is basically the mechanism dah. So this is already mechanism. So okay, so that's already mechanism. But if you want to show mechanism in terms of what we call picture orbital, this is the way lah. So normally when we talk about mechanism, what we want, let me remove the ink. When we talk about the mechanism, we just want this only. Okay, but if it's this also mechanism, but it show the orbital mechanism, how to show in the picture lah. So you can see here, curly arrow representation is like this. So this mechanism, but what happened in orbital level is like this. Okay, so you have sp2 hybridized carbon. So this sp2 hybridized carbon, and then we know the LUMO, the what we call the pi antibonding is this thing. So mean that the LUMO and HOMO will sort of like interact, the best interact with each other lah. So that's why the HOMO is nucleophile and LUMO normally is electrophile. So because the LUMO, the pi antibonding is at the carbon, so that's why the nucleophile will attack at the at this carbon lah. Okay, when you attack, look what happened. Look what happened when you attack this thing. The angle change. You see, from the planar, from the trigonal, this is what you call trigonal. This thing become tetrahedral. So remember, the reaction is not just editing, elimination or substitution. When the reaction happen, things can change in terms of structure also. For example, the trigonal planar change to the what we call the sp3 hybridized carbon. The carbon here adopt the sp3 hybridized, not this sp2 hybridized anymore. Okay, so this also the same thing, but this we talk about the pi antibonding lah. Here we talk about the pi antibonding here. Okay, but you can look, it just seem like this. It's more or less the same, but one they talk about the pi, one they talk about the pi antibonding. Okay. Okay, filling antibonding orbital breaks bond, pi bond broken, leaving only CO bond and electron from blah blah blah. The reaction is usually carried out in the presence of acid. This basically the idea of this is for the protonation lah, protonation. And so this protonation to give cyanohydrin. Cyanohydrin, this is cyanohydrin. The cyano and something else lah. Cyano is CN lah, the cyanohydrin. Okay, notice planar sp2 change to tetrahedral. Okay, so when the reaction happen, the structure of the molecule can also change. Okay, now let's talk about how Carbonyl Group is attacked by the hydride. Okay, this still nucleophilic addition. Previously we used cyanide, but now we use hydride. It's the same. It's just different reagent. Okay, when we use cyanide, on ketone or aldehyde, which carbonyl before that we looked before, there is nitrogen in the final alcohol product. If you look here, they are nitrogen. They are nitrogen here. So this is ketone. So this is ketone. This is ketone. This is ketone, and this is aldehyde. Okay, so either way, when you attack with the cyanide, you still have the nitrogen there. So what if we want the pure alcohol, mean that there are no nitrogen but just alcohol? Because we know this thing is already alcohol, this already alcohol, is still alcohol, but we want a pure alcohol without any nitrogen. How we get that? So one way is to attack Carbonyl Group with hydride ion. Hydride ion is what? Hydride ion is hydrogen with extra electron. So normally hydrogen you have electron, okay, but hydride here is basically you have nucleus and then you have 2 electron. So that's basically what does it mean by hydride lah. There are one extra electron. Normally hydrogen have 1 electron, but hydride mean that you have extra electron, and this extra electron, because they are 2, they can enter the orbital lah. They can sort of like fill in the orbital. Okay, so but hydride ion is so small. When this hydride ion is so small, hence the charge density is highly localized. Okay, what does it mean here? Because compare something small like this and then something very big. When you have something very big, the electron, if you have an electron, it will sort of like distributed, more or less distributed. Even though it's polar, it's still better distributed compared when you have very small. If you have very small, if this thing is polar or whatever, the electron will sort of like not really well distributed. It's sort of like localized lah. It have high density. If for example, let's say here, the electron is here, so we can say that the charge density is bigger here. And then if the electron move to here, the charge density is bigger here. So we call it localized. It's not like sort of like smear around. It's not like distributed. So when this thing happen, it's sort of like very it can act like a strong base lah. Because remember, when you have hydride, you have electron, and this electron is really highly localized. This thing will sort of like readily find target. Okay, find target to attack. Okay, because it's already at the brink of the atom lah. Okay, but if you are in the big atom, so it's not really as reactive. It's still what we call try to find, but it's not as really reactive as this hydride, which is small and localized. Okay, so okay, it's too much here. Let me remove everything. Okay, so look here. So meaning that this hydride ion is almost always react with the base. Okay, because it's so small, meaning that it's readily attack another what we call another proton lah. For example, this hydride ion is what we call act as a nucleophile. It will try to find the electrophile. So if you have this what we call halide here, So the what you call the halide, this thing, the electronegative fluorine or iodine or bromine or whatever, will sort of like pull the electron towards this atom, and then this hydrogen here will feel like deficient in electron. So this, what we call this hydride, will try to take opportunity to snatch this hydrogen in order to get H2 lah, to become H2. So that's why, because it's so small, then it's really, when you try to use the hydride on the whatever ketone or hydride, you not happen. Because why? Because before even this hydride attack this, it will easily attack the what you call this thing, this halide, the halide, whatever in the solution lah, in the solution. Okay. So strong base will readily react with the any available proton, because remember, H2O also have proton. You have O and then you have H. This hydride can also attack here. So solution, then this will be already consumed, so not enough for it to attack this thing. It's already consumed first by the water or by the acid. Let's say you have acid, this also the what I call the hydride will attack this thing. So not enough time for this hydride to attack this what I call the big stuff like the ketone or aldehyde. Okay. Why this happen? Why this is favored? Because remember, we learned in the class before, when you have something small, it's much more easier to attack something that is small. Is sama kufu lah, we call it. So for example, efficient overlap between orbital of similar size, 2p 2p, compared to this, when you have two different size, you want to overlap, it's difficult. Okay. There are more efficient overlap between orbital of same size, because if you compare this thing and this thing, compare this with this, you know this is much smaller lah. This thing is much smaller than compared to the aldehyde or ketone. So that's why it's much easier for the hydride to attack, to readily attack the water or the other stuff like the halide lah. So the question remains, how to get the pure alcohol? Okay. So let me remove the color first. So the question still remains, how to get the pure alcohol without this the nitrogen there. So they use reduction agent like sodium borohydride, NaBH4. Okay, we have seen before what is sodium borohydride. Is basically is boron, and then you have 4. So we have learned this in the previous class, I think. So basically sodium is basically Na borohydride. So Na become plus, this become minus. Okay, this become minus. Okay, so in this case, this thing will become the agent lah, in order to become this become what we call will become sort of like the nucleophile to attack. But remember, this negative here seem like oxonium ion does not represent lone pair or two electron lah, two electron. Okay, why? That's you need to read back. The analogy is the same with the oxonium ion, but it's the same idea, because boron is basically the boron itself. If you look boron itself, they have 3 valence electron, but here you have 1, 2, 3. It's already extra lah, extra. So they are negative, but then you need to remember this negative charge is not represent lone pair. So now when you want to do reaction, when this become nucleophile, the arrow will start from this, will start from the bond, not from the charge. Because when you start from the charge, what does it mean is that you bring the charge here represent 2 electron. So which is not right here lah. This negative here just mean that boron as if have 1 extra electron only, not 2. And also boron doesn't have a lone pair here. So that's why when you draw the reaction, nucleophilic reaction, when you use borohydride as a nucleophile, the arrow must start with the bond there. Okay, let's talk a little bit about reduction and oxidation, because previously we showed that in order to add a hydride ion to the carbonyl group, we need something that can provide this hydride ion, which is sodium borohydride. Sodium borohydride is basically the reducing agent. So it's good for you to know a little bit about reduction and oxidation also. Okay, so one thing we need to establish is that all functional group are different, but some are more different than others. So we can classify the functional group under this table under its oxidation level. So how do we know the oxidation level of particular functional group? Is by looking at the heteroatom. What is heteroatom? Heteroatom is basically this. Heteroatom is any atom in organic molecule other than carbon or hydrogen, and then look how many bond connect to the heteroatom. How many bond? Okay, so look here first. So you have this heteroatom. Okay, how many bond connect to the carbon? So you have one only. So how many? One only. This one only. And then if we go to the next one here, the aldehyde, you can see this is heteroatom. Where is heteroatom? So this heteroatom, how many bond connected to the carbon? So you have one, you have two. Same with this, one and two. The R here doesn't count as a heteroatom because it's basically alkyl. So alkyl is carbon. So we can say before, any atom in organic molecule other than carbon or hydrogen. So if you look then to this, what we call to the oxygen level for this carboxylic acid, we can see here the carbon, how many heteroatom? You have 1 and 2. But then how many bond to the heteroatom? You have 1, 2, and also 3. Same with this, 1, 2, and 3. So 3 bond to the heteroatom. So we call this thing, all the family that have similar bond to the heteroatom, we group it in one family. Okay, so alkene and alkene is a little bit different. Alkene a little bit different, but we see later lah. The carboxylic acid, ester, and amide can be changed into one another by reaction with simple reagent. So if let's say carboxylic acid, ester, amide, so this, and this, all in the same family. If you are in the same family, you can be changed into once another with a simple reagent. For example, you can convert carboxylic acid to ester, ester to amide using the simple reagent as water, alcohol, amide. But if let's say you want to convert the alcohol to here, this to here, then you need to use a reducing or oxidizing agent lah. Okay, so the same family can be interconverted without the need of redox reagent. Redox mean reduction and oxidation reagent lah. So look here, alkane and alkyne doesn't fit easily in this category as they are no bond to heteroatom. Okay, alkane can be made from alcohol by dehydration without any redox. So it's impossible to put in alcohol column. Same goes to the relation to the alkyne with aldehyde. Okay, so oxidation and reduction by itself is, what is it? Okay, oxidation is loss of electron. Okay, reduction is gain of electron. So some people use mnemonic Leo the lion say grr. Okay, so Leo the lion say grr. So Leo lose electron mean oxidation, gain electron mean reduction. So that's what does it mean lah, just mnemonic lah. Some people use oil rig, so mean that oxidation is losing electron, reduction is gaining electron. Is regardless what mnemonic you use, it doesn't matter as long as you know the losing electron is oxidation, whereas the what we call the gaining electron is a reduction. Okay, in organic usually the compound is ionic. Okay, in organic chemistry usually compound is ionic, okay, and have charge. Normally when we talk about the redox reaction, we talk about the inorganic chemistry. So for example, this video, let me put the video first. This video, okay, let's see this video. If you look, this video is a reaction. So let me play this video. So you have this, what we call this the sodium nitrate. Let me play first. Okay, so I have an arrow for that. So you can see there, where is the thing? Okay, this is silver nitrate, this is copper nitrate. Okay, so now silver nitrate is AgNO3. this is copper nitrate, Cu whatever the thing lah. But the idea now is that this thing can be reduced to this thing, silver nitrate, can be reduced to the copper nitrate. But this experiment just to show you what is copper nitrate looks like, okay, what silver nitrate looks like, and how the reduction occur. So if they put the cut, okay, let's say they do this, so when they put the what we call the powder of silver nitrate into this, dissolve it, you get this. When you put copper to nitrate into the solution, you get this blue color. Okay, so if let's say this AgNO3, so silver nitrate, to be reduced to this beaker will change color into blue. So how to do this thing, how to reduce the silver nitrate, is to use copper. So you add copper. So how you add copper, you just add copper wire there, and then over time the copper wire the reduction and oxidation will happen, redox reaction will happen. So when this thing happen, the reaction happen, the silver nitrate, remember the silver nitrate is the solution inside this thing, it will be reduced to copper nitrate. So that's why they change color, the same color like this lah. So just to show you that this is typically what does it mean by what you normally associate the reduction and oxidation. Normally when in your primary school, maybe you have done this experiment, they use the color change and so on. Yes, that's true, but that's more towards inorganic chemistry, because this AgNO3 is inorganic. You can see this Ag is metal and O3 is non-metal, so this is organic, this is an inorganic compound. Okay, so let me go back to this. Okay, so that is this YouTube. So I put the link there, you can open it for you to look further. And then what else? And then this silver nitrate react with copper to form copper to nitrate and silver blah blah blah. And so this is basically what we have seen before lah. So in organic chemistry, reactant and product usually covalently bonded and have neutral charge. Okay, when we talk about the inorganic reaction just now, the redox reaction that we see in the YouTube just now, that is basically between inorganic, between the ion lah, between solid ion. But in organic chemistry, the reactant here, the reactant and the product usually covalently bonded. Okay, AgNO3, when you dissolve, you get Ag plus and NO3 minus. But when you put the organic compound, okay, organic compound doesn't have this thing, doesn't have this what we call the charge. They normally they just, you put sugar in the what we call in the water. This still sugar. It's not like dissociate like that. Okay, so but then Luger, I mean that the concept of reduction and oxidation is still valid, but now we focus on electronegativity. Okay, let me remove the color first. This too much. Okay, how is so? Look here. Okay, so for example, let's say you have this alcohol and you do oxidation. What do you see happen? What you see is that the hydrogen will be removed. Okay, hydrogen will be removed, and then the bond will be what I call, let me show, oxidation, replacement of carbon hydrogen or carbon bond to more electronegative heteroatom. So if you look here, this is oxidation. Why? Because remember, oxidation is what? Oxidation LEO, meaning that oxidation is lose electron. Okay, so this is what we established before, lose electron. So how the electron lose here? Okay, how can we say the electron is losing here? So if you look here, the carbon here at the beginning is happy, because for example, they are equally distributed. The electron of the carbon here, they are equally distributed, although they are more electronegative, but it's still equally distributed. But then when you turn into this, the carbon here, they are attached to only O. Let me put the color. They attracted to the density, the electron density of the carbon here will somehow attracted to the O, because O is highly polarized. So here is as if the carbon lose the electron. Okay, the carbon lose the electron because the what we call the electron density is pulled away from the carbon. So that's why in organic chemistry, the oxidation is as if the carbon here lose the electron by this way lah, by, for example, by making the bond to the more electronegative electroatom. Okay, so this is example of how from sigma bond become the what we call the pi bond. Okay, so this is an example of elimination reaction. Okay, in oxidation, this thing, the hydrogen does not literally mean hydrogen gas is liberated. Okay, because this process requires some oxidation agent. For example, KMNO4, CrO3. So this example of oxidation agent lah. So we talk about reduction. Reduction is the reverse lah. So reduction is replacement of the bond to electronegative heteroatom with the CC bond. So if you look here, the carbon here, at the beginning, they feeling that their electron is attracted to the nitrogen, mean that the electron here is less. But then here, if you see the what we call the product here, the carbon here, the same carbon here, they are feeling that the electron density is donated back to him. Okay, so because when you change from the double bond to here, there are no more what we call, there are less what we call less electronegativity happen lah, even though they are still electronegative here, but they are less because they are they are equally distributed. So this feel better lah, as if the electron density is donated back to the carbon there. So this is gel lah. So as if gain electron. So the carbon here, as if when they do this reaction, the carbon feeling that is gaining some electron. So that's why this is what we call the reduction. Okay, so here we can say that the pi bond goes to the sigma bond. So this addition. Okay, during addition, this H here, normally we don't use H lah. During reduction, we use the what we call, we use the reducing agent lah. But there are sometimes we do use the hydrogen gas lah. But if we do use hydrogen gas as a reduction agent, reducing agent, we need to do it for weaker double or triple bond in alkene and alkyne with the presence of catalyst, meaning that there are some reaction they use hydrogen gas in order to reduce something, but normally that's only apply for the weaker double or triple bond, as if in alkane or alkyne. Okay, typically the reducing agent, for example, this for this amide, they is hydride. Okay, for example, they use this lithium aluminum hydride or sodium borohydride, like we say before lah. So when we talked before about the reduction and oxidation between the families of the functional group, this is what we mean lah. For example here, if you have alcohol, aldehyde and carboxylic acid, these three functional group is not in the same oxidation level. Okay, so when it's not in same oxidation level, in order to go to alcohol to go to aldehyde, aldehyde to go carboxylic, you need to use what we call oxidation. Okay, and then when you go from carboxylic want to go to aldehyde, you need to do reduction. You need to use reduction agent lah, reducing agent. Same with aldehyde to alcohol. Okay, because why? Because if you look here, you have hydrogen. What does it mean by oxidation? Oxidation means that losing. Oxidation here, lose electron, mean that lose hydrogen lah, lose hydrogen. So that's why they can lose. So that's why one hydrogen lose here, and then you do further oxidation, this hydrogen will be loose. That's why no more. It become OH there. It become OH. Okay. Okay. Reduction is other way around lah. You add hydrogen or electron lah, in the way. So if you look the secondary alcohol, if you look at secondary alcohol here, secondary alcohol, you have hydrogen, one hydrogen. Okay, so when you do the what we call oxidation, remember oxidation is losing the electron, mean that losing the hydrogen lah. So when it's loose, it become the ketone. Okay, and then this ketone can go back to this thing by adding the hydrogen lah. That's why from ketone to here to secondary alcohol, you have the hydrogen. But if you use tertiary alcohol, this is not hydrogen, this is not hydrogen, this is not hydrogen, this is what we call the alkyl group. This is CH3, 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 CH3. So there are no part for secondary alcohol to lose its own hydrogen lah on for this alcohol. So they cannot undergo the oxidation. Nothing will happen lah. Okay, let's talk about the example of reduction and oxidation. So you can have this thing. So what is this? So this is carbon. So carbon, you have oxygen, and then you have R, and then you have R. So this is ester, and this one is also R, and then you have OH there. So basically this is alcohol. Okay, so you know that ester is basically you can see there are like 1, 2, 3 bond to the heteroatom, while the alcohol is only 1 bond. So you know that different family, so you will need to use a reducing agent in order to get from ester to alcohol. So this is example of reducing agent, which is lithium aluminum hydride, same like before sodium borohydride. So both sodium borohydride and lithium aluminum hydride is ionic compound. So when you put in the water, it will dissociate to lithium plus and aluminum hydride. So this aluminum hydride, so Al, ash, and ash, and then you have minus, is the one that will perform the nucleophilic attack lah. So here the negative charge here doesn't mean there are 2 electrons. So this thing, you need to start the nucleophilic attack from this bond. Okay, so for example, ester reduction to alcohol is this. So let me remove all this thing first before, so that you can see easily. So the first thing, as usual, the nucleophilic attack the electrophile, which is the ester, and then it will cause the bond to be break, and the oxygen will be become an ion. Okay, we got gain a negative charge, and then the leaving group removal. Okay, so leaving group removal is that we will discuss further later on, but basically what happened here, this is addition, and certain addition reaction will not finish by addition only. In this case, this is elimination. So you have addition of the aluminum hydride to the ester, and then because this, what we call the ester have this leaving group, the OR will be eliminated. Okay, so here is the case of the reaction. You have 2 reaction in one: addition, elimination, and then when this what we call the meaning of leaving group removal is in this case, the OR is a leaving group. This thing will be moved out. Okay, it will not coming back. Okay, so that's why you get this thing. Okay, the detail we talk later lah. But basically, this is what happened. And then after that, this thing, the aldehyde that is produced is basically electrophile, because if you look here, the carbon and the oxygen, they are partial positive. So this meaning that this is deficient in electron, so it can behave as a electrophile. So we know that nucleophilic addition of this sodium borohydride, aluminum hydride can occur to the do stuff to the electrophile. So this aluminum hydride will attack the aldehyde, and the same thing happen, the oxygen will gain the negative charge, and then you get something like this. Okay, so now this oxygen here still gain a negative charge. Now still the salt becomes salt. So in order to get alcohol, you need to change this salt into the alcohol. So how to get that is to bring the hydrogen, the proton, so that this negatively charged oxygen will get protonated. So that's why they add the water here, okay, so water, or in this case also this ozonium ion. So basically when you add water, this oxygen will get protonated. If you look here, protonated in work up step, as if there are 2 different steps, which is true. If you look here, they are number 1 and number 2, meaning that in order to do this reaction, in order to get alcohol, you need to finish this first. Okay, you need to finish this first. Only after you get this, only then you add water. Okay, if not, if you don't do like this, if you put water straight away together with the lithium aluminum hydride, what will happen, this lithium aluminum hydride is the one, so this Al, ash, okay, so this will sort of like OH. So this will attack this. Okay, this will attack this. So the reagent, the reducing reagent will be destroyed. Okay, if they are add together. So that's why you see number 1, number 2. Meaning that number 1 here meaning that you need to complete this reducing process first, only and only then you add water. Okay, so that's why protonation in workup step. Okay, workup step is the second step is done after the first step is finished. Normally they add the workup step. Normally they add the dilute acid or water in order to protonate the oxygen here. So when you protonate the oxygen, you get this alcohol. So that is basically ester reduction to alcohol.